Hello again, everyone. In today's lesson, we're going to start looking at specific types of energy, and we're going to be starting with mechanical energy. Mechanical energy is still within the concept of motion, therefore it follows nicely with the other stuff that we've been looking at recently. There are two different types of mechanical energy: gravitational potential energy, which is energy based on height, and kinetic energy, which is energy based on velocity. Now, there's some pros and cons to using energy in questions that deal with motion. The pros, and it's actually a pretty big pro, is that the path taken by the object doesn't usually matter. All that matters is the starting and ending situations of the object. So you could take an object and lift it off the ground and zigzag it up and down or left to right as you're lifting it, and the zigzagging doesn't matter. The only thing that's going to matter is where did the object start and where did the object end. We're going to see later on an example where we're talking about a projectile. We've already looked at projectile motion in a previous unit. You can actually solve certain aspects of projectile motion using energy concepts. However, if we look at the cons now, the only problem with that is energy isn't going to give you directions in your answer. It's just going to give you magnitudes. So it doesn't replace all of the knowledge you know about projectile motion. It just complements it. There are certain situations where you don't need to know the direction of the object, and in that case you can just use the energy concepts to be able to solve the problem. So let's look at gravitational potential energy first. We've already seen that if you want to lift an object up off the ground, that requires a certain amount of work. And energy is just the capacity to do work. In fact, you can say that work is equal to energy. So if you know the work equation, you also know the energy equation. And we're actually going to use work for both gravitational potential energy and kinetic energy. We're going to derive the equations from the work equation. So as we've seen before, W is equal to F dot D. Now we're talking about an object being raised directly straight up from the ground. Therefore, I'm not going to be using the vector symbols on top of the F and D in this lesson. We've seen in a previous lesson that it's actually F dot D, which is F times D times cosine theta. But because the direction of the motion is in the same direction as the force here, theta is equal to 0, cosine theta is equal to 1, so we're just left with F times D for our work equation. And if we replace W by potential energy, EP, and we replace F by MAG, because we're working against gravity, which is the force of gravity, MAG, the D is going to be a height, because we're lifting the object. So if I draw a little picture of this scenario, we've got an object here that we're lifting up to a certain height. The height is the displacement or the distance that the object is taken. The force that we're acting against is the force of gravity to lift it up, and therefore that's why we get MAG times H. It's the exact same thing as F times D. Now, I've seen in certain textbooks potential energy, sometimes they will use the letter U to represent potential energy. I have no idea why. I find that extremely complicated for no reason, but I figured I'd better mention it because I have seen it enough in university texts recently that it should be mentioned. So an easy little change of variable if you get to that point and you need it. Just be aware that sometimes potential energy is not going to be written as EP, but that's what we're going to do in this course. Okay, so what happens when you lift an object up is you're actually storing energy. When this rock or object is up in the air, just waiting to be let go, once it's let go, it could do work on something that it was going to hit. So let's say we had a spike down here that we had to drive into the ground. You could lift this object up, drop it onto the spike. The spike would then feel a force driving it into the ground, a certain displacement. Force times displacement is work. So there's stored energy here in this object. and that is called gravitational potential energy. So any object that has a height with respect to another height, if it's higher than that other reference point, it is going to have potential energy with respect to that reference point. So if you have a shelf in your room and you have an object up on top of that shelf, if that object fell off the shelf, it could perform work on something that it was going to hit, specifically your head in an accident scenario, which would hurt, but that is the object doing work on you. I have the example here of a hammer. If you lift a hammer up in the air ready to hit a nail, that hammer is going to store or have stored in it potential energy ready to be used. So here's an example of a problem that you could be asked. How much potential energy does a 4 kilogram object have if it is raised 3 meters above the ground? So if we draw a little system diagram here, we've got our object being raised 3 meters above the ground. Its mass is 4 kilograms. We know that the potential energy is equal to the force times the displacement, or we can just write m ag h. Now, another thing in certain textbooks that you will see is they will write it as m ag delta h. The delta just means the change in height. Now, we can choose the reference point of 0 as being the surface of the Earth, which we usually do. And delta H, as you know, is H2 minus H1, but if H1 is 0, you're just left with H2, which we can just call H. However, if you're starting at a height that isn't 0, and we're probably going to look at an example of that soon, then the concept of delta H is a little bit more important, but we'll get to that at that point. So it's a very simple equation to use. Just make sure that you are in the MKS system. So if ever a mass is given to you in another unit besides kilograms, you must convert it to kilograms first. But we have kilograms here. Same thing with the distance. If the distance is not given in meters, or the height in this case, you must convert it to meters, but everything is good to go here. So we've got 4 times 9.8 times 3 meters. And if I take a calculator here, I'm just going to do this off screen if that's okay. 4 times 9.8 times 3 is equal to 117.6. And just like with work, oops, sorry about that. I start talking and make a mistake in the numbers. 117.6 joules. Now, I want you to notice that energy, work, do not have a vector symbol on top of them. Even though force and displacement are technically vectors, when you do the dot product of two vectors, you never ever end up with a vector, you end up with a scalar. So work and energy do not have vectors on them. So we have no worries about a distance here. You'll notice that I didn't put the negative for the 9.8. So because we're not talking about vectors, we're talking about scalars. And you could definitely write this in the proper format for significant digits. We only have one significant digit here, so we would have to write that as 1 times 10 to the 2 joules in this case. Okay. So here's another example. In the sport of pole vaulting, the jumper's center of mass must clear the pole. Assume that a 59 kilogram jumper must raise the center of mass from 1.1 meters off the ground to 4.6 meters. And here's a case where we're not starting at 0. Okay. What is the jumper's gravitational potential energy at the top of the bar? So this is also kind of a scenario where the topic of energy and the fact that it doesn't require the knowledge of the path that the object is taken is going to come into consideration, because a pole vaulter, if you think about the pole vaulter's path, a pole vaulter doesn't technically go straight up in the air. There's going to be a little bit of a parabolic curve to the path that the pole vaulter is taking, but all that we need to know is what was the original height, which is 1.1 meters, what was the final height, which is 4.6 meters, and we're going to be able to calculate the gravitational potential energy at the top of the bar. So gravitational potential energy is equal to m ag And in this case, I'm going to say delta H, because we're going to calculate the change in height of this position. So you might be wondering, yeah, but sir, isn't it still going to be the gravitational potential energy with respect to the ground, because we are going all the way up to this height? Well, the problem is we didn't start at the ground. So there was already some energy in the fact that the starting position is here. Like technically you could say, how much energy did we use to raise the point here? Well, we didn't use any energy to raise it there, because that's where the person's standing. That's the center of gravity, right? It's like for a male, it's in the chest, and for a female, it's in the hip area. So it's already a certain height. So we're only changing the height from this value to this value. So we're only storing that amount of energy. We're not actually storing any energy to bring it from the ground up to this point. So that's why we have to use the delta H here. So our mass is going to be the pole vaulter's mass, which is 59 kilograms. Acceleration of gravity is 9.8 meters per second squared. Delta H is H2 minus H1. So that's going to be 4.6 minus 1.1. Now you could do that off to the side and then bring it into the equation. However, if the number was really, really ugly and you had to round, you wouldn't want to do that. So I'm going to do it all within the same equation here. So I'll do the calculation off to the side. So 59 times 9.8 times bracket 4.6 minus 1.1. And the answer is going to be 2023.7 joules. And again, looking at our significant digits, we have basically two significant digits. Even though we have a subtraction here, remember when you're subtracting values, it's the number of decimal places that's important. Well, both of these numbers have one decimal place. So they would round off to one decimal place, which would make it still have two significant digits. Everything has two significant digits. So our answer here would be approximately 2.0 times 10 to the 3 joules. And that's how much energy you're storing from bringing the center of mass from this height to this height. And it doesn't matter that it's a bit of a parabolic path. All that matters is the starting height and the ending height in this case. So with the hammers example, we can lead into kinetic energy, because energy, and we're going to talk, we've already talked about this, we're going to talk about it all the time. Energy has to be transformed from one form to another. You can't destroy energy, it can only transform. So when you lift a hammer up, as you start to bring it down, you're going to give that hammer some velocity. You're also lowering it, so it's going to lose some gravitational potential energy, but that loss is turning into velocity, velocity energy, okay? So we say that the gravitational potential energy is transformed into kinetic energy. So with kinetic energy, again, let's see how we would derive the formula for this. So we know that work is equal to force times displacement, and work is also energy based, right? So we can replace force by ma. Now this time I'm not using the acceleration of gravity, because we're talking about an object that's moving in a horizontal line in this case, and just to make things simple, okay? So there's going to be, and it could actually be vertical, it doesn't actually matter. There's going to be a change in velocity, so it's going to be accelerating, okay? But it's not necessarily gravitational, so I want to make sure that this is a general equation that'll work for any scenario. So we're just going to use d to represent any displacement. We know, because we're going to velocity, that we somehow have to make velocity appear in the energy equation. Well, where else have we seen an a times a d? Well, if you look at this equation, there's an a times a d in this equation. If I isolate time for the a times the d, I just move the v1 squared over and divide by 2, and I get this. And now I'm going to substitute that into there. And what we end up with is Ek, the kinetic energy, is equal to m times v2 squared minus v1 squared over 2. And if we distribute the m into the numerator, we end up with what is called the kinetic energy equation. Kinetic energy is equal to the mass times the second velocity squared divided by 2. minus the mass times the first velocity squared divided by 2. So what'll often happen, sorry, let me go back a slide here. What'll often happen is we're still going to usually, or often talk about the fact that the initial velocity was 0. So if the initial velocity is 0, this whole term becomes 0, and we're left with just mv2 squared over 2. So let's look at this example and I'll explain that a little bit more. So it says find the kinetic energy of a 48 gram dart traveling at a speed of 3.4 meters per second. Well, what was the original speed of this dart? The original speed of this dart was 0. So if I put v1 equals 0 in this equation, this whole second term disappears, and we're just left with ek is equal to m times v2 squared over 2. That's going to happen quite a bit. It doesn't happen all the time, but anytime you're just given one velocity, you're just going to write ek is equal to m times v2 squared. Oh, let me fix that v. All divided by 2. Because v1 is equal to 0. Okay? So that's assumed when you're given a problem like this. Now we do have a problem that our 48 grams is not given in the proper unit. So let's fix that. To convert grams to kilograms, we divide by 1,000. So that's going to be 0.048 kilograms. So we're going to just plug that in here for our mass. Our velocity is 3.4 meters per second squared. And we divide all that by 2 because of the formula. So again, I'm just going to do this off screen. And that's giving me 0.27744, which I'm just going to round to 0.28 joules. So that dart is going to have 0.28 joules of energy if it's traveling at that speed. Again, no vectors because energy does not have a vector on it. So let's take a look at a scenario where we're talking about the law of conservation of energy. Again, energy can only be transformed, right? So this question is saying, as the water in a river approaches a 5.7 meter vertical drop, its average speed is 5.1 meters per second. For each kilogram of water in the river, determine the speed at the bottom of the falls. So the first thing we need to do is we need to really understand, what do we mean by the energy transforms? And also, what do we mean by the total energy that the object has in a specific part of the problem? So what kinds of energy does each kilogram of water have at the top of the drop? Well, it tells us in the question that the speed of the water is 5.1 meters per second at the top of the drop, and it also has a height of 5.7 meters at the top of the drop. So we need to find the total energy at the top of the falls and make this equal to the total energy at the bottom of the falls in order to be able to calculate the speed at the bottom of the falls. Again, note that it doesn't matter the path that the object's taking. The velocity at the top of the, for the water at the top of the falls is horizontal. It's going to be dropping vertically. That doesn't matter. So I'm going to do two things here. We're going to talk about the top of the falls. We're going to talk about the bottom of the falls. We're going to separate that in two. At the top of the falls, if this is my, I think it was 1 kilogram, right? Yeah, for each kilogram. So this is my mass of 1 kilogram of water. It has a certain velocity and it has a certain height. Certain speed, I should say, sorry. Actually, let me fix that because we're not talking about vectors here. My mistake. So it has a certain speed and it has a certain height. Therefore, it has two different types of energy. If we talk about its total energy, we have to add both the kinetic energy plus the potential energy together to find what the total energy is. So let's do that. What is the total kinetic energy? Let's start with just kinetic energy. So kinetic energy, as we saw on the previous slide, is mv squared over 2. The mass is 1 kilogram. The speed is 5.1 meters per second. That's squared. That's all divided by 2. So that's going to give us 5.1 squared divided by 2. It's 13, almost exactly, joules. It also has potential energy, which is MAGH. Now, we don't need the delta here because they didn't tell us that the bottom of the falls is at a higher height than 0. So we're going to assume that the bottom of the falls is at a height of 0. Okay, so falls fall down here, and this is going to be our reference height of 0. So again, we have 1 kilogram. Our AG is 9.8 meters per second squared, and our height is going to be the height of the falls, which is 5.7 meters here. And 9.8 times 5.7 gives 56 joules if we round that off. So our total energy at the top, so we'll call that E total 1, is equal to the sum of those two. So 13 plus 56, and that's going to be an approximation, is 69 joules of energy at the top of the falls. Okay? For the energy at the bottom of the falls, well, what kind of energy does the water have at the bottom of the falls? So let's call this E total 2. I should have put a 1 here on this one. Well, does it have any more gravitational potential energy? It's reached the bottom of the falls. So the water at the bottom of the falls doesn't have gravitational potential energy anymore. That's gone to 0. So the only type of energy it has is kinetic. So we can say that the total energy here is just mv squared over 2. Well, if you look at what we were trying to calculate, they asked us to determine the speed at the bottom of the falls. Well, that's our only variable now. Because we know the mass, the only variable is v. I need to make this equal to something on this side so that I can actually isolate v. Well, the total energy before has to equal the total energy after. So we can write that E total 1 has to equal E total 2 because of the law of conservation of energy. So I know that 69 joules has to equal mv squared over 2 at the bottom of the hill, or at the bottom of the falls. Isolating for v, we'll get 2 times 69. The 2 will come over here and multiply. Divided by our mass, 1. And then we're just going to square root that to find our velocity. And this can all be done because of the law of conservation of energy. You calculate the total energy before, which is just the sum of all of the energies that are involved. Kinetic and potential are the only two in this case. You look at the other side and you do the exact same thing. You realize that at the bottom of the falls, the gravitational potential energy is 0. The only thing that's left is kinetic energy. You make the two total energies equal to each other, and then you just isolate for the variable you're looking for. So the square root of 2 times 69 approximately 11.7, which we can round off to 12, and that'll be meters per second. So that is how the law of conservation of energy works. this is the question I was mentioning earlier. Determine the speed of the basketball as it goes through the hoop. So this is clearly a projectile motion scenario, but it doesn't matter what the path the ball is taking. All that we need is the initial conditions and the final conditions, and we can calculate the velocity going through the hoop. Or sorry, my mistake, the speed going through the hoop. You'll notice that there's no direction given on this initial speed, okay? So that's what makes this a bit of a con. We're not, instead of a pro, when we're dealing with energy, we can calculate stuff like this, but we're not going to get the direction, all right? If we were doing this with a projectile motion scenario, we'd also get the direction. But you'll notice that they didn't give us any angle here, so we don't even know what the initial direction is. We just have an initial velocity. So once again, if I set this up as E total 1 equals E total 2, this time I'm going to do it a little bit more algebraically, just to show you a slightly more advanced way of solving this kind of problem, because you really shouldn't be inputting numbers into an equation until you're ready to type it into your calculator. All of the work should be done algebraically to minimize the amount of rounding problems you're going to encounter, okay? So what is the total energy before? Well, what kind of energy does the ball have? The ball has kinetic energy because of the velocity, or the speed, sorry. The ball has gravitational potential energy because of its initial height. So we're going to say EK, I'm going to call this EK1 plus plus EG1. So the two first energies, the first kinetic energy and the first gravitational potential energy. And at position 2, what kind of energy does it have? It has both again. It has EK2 for the second position plus EG2 because of the second height. Okay, the kinetic energy at the second position, the gravitational potential energy at the second position. We are looking for the velocity, or the speed, sorry, at the second position, which is going to be contained in EK2. So we can start to rearrange this equation right now. We need to get EK2 isolated, which means EG2 is going to come over to the other side. Now if I write it with EK2 first, EK1 plus EG1 is going to stay the same. And we're going to subtract EG2. So watch what's going to happen here. I'm going to replace all of these by their corresponding equations. So what's EK2? EK2 is going to be mv squared over 2. Now we need some way of indicating that this is the second kinetic energy, not the first one. So I've seen different ways of doing that. One of the symbols you'll often see is they'll put a little quote next to here, which means prime. That's one way of doing it. You can say the second velocity in the second position, so you can put a little 2 there. You just got to make sure you understand that it's not the second velocity from the first position, if that makes any sense. It's the second velocity from the entire scenario, okay? I prefer to do this myself. I don't think that should bother anybody, I hope, and you'll notice that they even called this V2 up here anyway, so it kind of matches what we're talking about. EK1 would be mv1 squared over 2. EG1 would be MAG H1. Now they called it Y1, okay, which is the height. I'm going to call it H1 to follow the same conventions that I was using earlier. And we're going to subtract MAG H2. Again, they called it Y2. I'm just going to call it H2. Well, here's one of the nice things about using algebra. Every term has an M on both sides of the equation. And because of that, all of the M's can be divided out. You could factor out the M on this side and then divide both sides by M, and all of the M's cancel out. There's a couple of other neat things that we can do. Notice how you have an AG H1 minus an AG H2 here. You could also factor that. This is just a little bit of more advanced stuff. You don't absolutely have to do this. but it's nice to see. You could write it as h1 minus h2 here by factoring out the ag. Okay. So let's see what happens here. We could isolate it even more by multiplying everything by 2 now, because we're trying to get v2 all by itself, right? So we're going to have to multiply by 2 at some point and then square root. So we could actually multiply everything by 2 right now. If we do that, we'll get just v1 squared here plus 2 ag h1 minus h2. This just reduces how many numbers we have to put in here, and it might allow us to do some of the math in our head. And then we're going to have to square root. So let's just do this at this point. So v1 was 7.2 meters per second, and that's squared. .21 is h1. ag is 9.8. I already forgot what it was. 2.21 minus h2, which is 3.05. And I'm going to do some of this calculations off screen here. So 7.2 squared plus 2 times 9.8 times bracket 2.21 minus 3.05 is going to be equal to 35.37. So you'll notice that the only time I inputted numbers is at the very end when I'm ready to put it in my calculator. I didn't round anything off anywhere else. At this point, I'm going to square root that value, which gives 5.94. I believe everything had 2. Yeah, the least amount of significant digits is 2. So we're going to round that off to 5.9 meters per second. And let's see if that makes physical sense. Does it make sense that the second speed as it's going through the hoop would be less because the initial speed was 7.2? It should make sense because you're slowing down, slowing down, slowing down, slowing down, and then you're going to start to speed up, speed up, speed up, but you're not reaching the same height you were at. So you're going to have a slightly less large speed here, which does make physics sense. So this is a slightly more advanced way of doing a law of conservation of energy problem. It is a better one though, and if you are planning on going to university at some point, this will be the way that they do it. They usually will not want you to put numbers in until the very end, until you've carried all of your variables all the way to the very end. I'm hoping it's not too difficult. Let's just quickly recap here. We found our total energy at the first position, which is kinetic and gravitational potential energy. We found our total energy at the end, which is kinetic and gravitational potential energy at a different height. We don't know our second kinetic energy, but that's what we're looking for. We're looking for the speed, which is trapped inside of that part of the equation. We rearranged everything to get the EK2 all by itself. We replaced EK2 by its corresponding equation. Same thing with EK1, same thing with EJ1 and EJ2. I showed that you can cancel out all the m's. That just makes the math a little bit easier. I also discussed the fact that because we're trying to isolate v2 squared, we're going to have to multiply everything by 2. So every term on both sides gets multiplied by 2. That means the 2 disappears here, the 2 disappears here, and then there's a 2 that appears in front of the 2ag, in front of the ag, I mean. And then it's just a matter of plugging in all the numbers and using your calculator to find the answer. If you wanted to, you could have plugged in all the numbers for EK1 here, all the numbers for EG1 here, all the numbers for EG2 here, then rearranged. But as I mentioned before, this way is a little bit cleaner. So one place that you will find the law of conservation of energy in your real life is on roller coasters. If you think of how a roller coaster works, you usually have a major hill and then you'll have all the different types of things going on in the roller coaster. To get up the hill, you're going to have a motor that's going to pull the train of the roller coaster up to the top. But at that point, there is no longer any propulsion on the roller coaster. It has its maximum gravitational potential energy and no kinetic energy at all, if any. As it comes down the hill, that gravitational potential energy is going to get really small, and the kinetic energy is going to get really big, and you're just going to have these exchanges between gravitational potential energy and kinetic energy. At the top of the hill right here, it's going to have a combination of both. It's going to have gravitational potential energy and kinetic energy. Now, the roller coaster will be losing energy due to friction. So that is like basically being lost as heat throughout the thing. So at some point, the roller coaster does have to stop. And that is why you need a motor to lift it back up the hill, right? Some roller coasters even have motors along the roller coaster to bring it up other hills because it doesn't have enough energy to do it itself. But most coasters will come around. By the way, I'm drawing the Dragonfire here. If you've ever been to Wonderland, okay. I didn't draw. I think there's a corkscrew somewhere in there as well. But that's basically how roller coasters work. They work completely off of the law of conservation of energy. Let's talk about efficiency. So efficiency is the ratio of useful energy provided by a device to the energy required to operate the device, and it's usually written as a percentage. So this is the equation for efficiency. Because you're going to lose energy to things like friction and stuff like that, you're never going to have 100% efficiency in a real world situation. So let's look at an example. A family uses several planks to slide a 350 kilogram piano onto the back of a pickup truck. The box on the back of the pickup truck is 81 centimeters above the ground, and the planks are 3 meters long. An average force of magnitude 1500 newtons is required to slide the piano up the planks. Determine the work done in loading the piano, calculate the efficiency of the planks as a simple machine to load the piano, and discuss where does the rest of the energy go. So it refers to figure 4 here. This question comes directly out of your textbook. I'm just going to draw the figure, okay? So here's your plank. Here's the back of the truck. Here's the piano. Here's the person pushing the piano. Okay. So why is there going to be a discussion of efficiency here? What is the most efficient way to get the piano into the truck? Well, the most efficient way to get the piano into the truck would be to lift it directly upwards and onto the truck. But that's really hard to do because the piano is so heavy. And they talk about simple machines here. There are quite a few different simple machines that you can use in the real world. A ramp is one of them. You also have pulleys. You also have levers. So there's a lot of simple machines out there that can make our jobs a little bit easier. So instead of lifting the piano straight up from the ground into the truck, that's what the plank is doing. However, we're losing some energy by doing that. So let's discuss how we figure that out. Well, you'll notice that they tell you what the average force is to slide the piano up the planks. Okay? Remember that work is equal to force times displacement, and work is just another way of talking about energy. So if we figure out how much work is being done here, it's 1500 newtons times the displacement, or the distance traveled, which is 3 meters. Now again, these are vectors, but because the force and the displacement are both in the same direction here, the force is up the plank, the displacement is up the plank, that means the angle between the two of them is 0, and cosine 0 is going to be 1. So it's basically just 1500 times 3 times 1. And and I believe that's 4,500. I'm just going to double check because my brain is not working right now. Yes, so it's 4,500 joules of energy. Okay, now how much energy would be required to just lift the piano directly into the back of the truck? By the way, this is part A, which is what they were asking us to calculate here, the work done in loading the piano. Well, the back of the truck is 81 centimeters above the ground. So let's calculate how much energy it would actually be required to just lift the piano straight up into the truck. Well, that's basically calculating the gravitational potential energy, because it's just a change of height, right? So that's MAG times H. The mass of the piano is 350 kilograms. AG is 9.8. And the height is 81 centimeters, which we have to convert to meters. So that's 0.81 meters. If I calculate that, remember, this is the most efficient way of getting the piano into the back of the truck. That gives 2,278.3 joules, which you can see is a lot less. So that means that we're losing energy by sliding it up the plank. It's making it easier. The amount of force required is a lot less, but we're losing energy. So what is the efficiency? Well, efficiency, if we look at the formula, is equal to what is the useful energy output divided by the energy input times 100. Well, which one is the useful energy output? The useful energy is the 2,778.3, because that's how much it would take to actually lift it up normally, directly straight up. Okay, so that's your useful energy. How much energy did we put in to doing this? We put 4,500 joules of energy. And you'll notice that if I put joules and joules here, they cancel out. That's times 100%. And if we do that calculation, you end up with a 62% efficiency. I don't have to write that word again. 62% efficiency in doing this. Where did the rest of the energy go? Well, the rest of the energy is going to be wasted as thermal energy or heat energy due to friction. And there's 38% energy wasted to friction. Let's look at another problem. A pulley system is used to raise a load in a shop. A force of 30 newtons is required to raise a mass of 70 kilograms by a height of 0.5 meters. If this requires 15 meters of rope to be pulled, what is the efficiency of this pulley? And I give you a hint here, and I say a lot less force is used because of the pulley system. So let's first start by talking about how much energy would it take to raise this load directly upwards, the amount of distance that it's saying that it's being raised. So we've got a 70 kilogram mass. And we know that the equation is MAGH. Now, what we can't use here is we can't use the force of 30 newtons. That's why I gave you this hint, all right? This is how much we're pulling on the pulley, but pretend there was no pulley. Similarly to what we did on the previous question, when we kind of pretended there was no plank, right? What's the most efficient way of raising this thing? It would just be to grab it and lift it straight up in the air. So our mass is 70 kilograms. Our acceleration of gravity is 9.8, and our height is 0.5. Let me erase the units here, actually. And we know that our final unit is going to be in joules here. So we've got 70 times 9.8 times 0.5. and that gives 343 joules. Now, how much work are we actually doing to raise this with a pulley system? Now, let me just quickly explain how the pulley system works. Okay, there's two different types of pulley systems. There's actually multiple types of pulley systems, but there's two that I want to discuss for this question. If you have a pulley with just one rope going over top of it, all that pulley is doing is changing the direction of the force. Okay, now that can be helpful if you don't want to pull straight up on something. In this way, you'd be pulling down on it, but you are actually going to have to pull with the exact same force as if you had to lift this mass straight up in the air. There is no benefit in force here. But there are other types of pulleys called block and tackle pulleys. And block and tackle pulleys will have ropes wrapped around them multiple times. And that actually is going to cause the fact that there's going to be 2 ropes pulling on this mass, or 4 or 6, depending on how many times the rope is wrapped around the pulley, which actually helps you to raise that mass up. It reduces the amount of force you have to do by half every time you add an extra rope. So 2 ropes is going to be half of what it was, 4 ropes is going to be 1/4 of what it was. So it can really help lift heavy objects. The only problem is you have to pull more and more and more rope to get these to work. So if we look at this question up here, I'm telling you that you're using a force of 30 newtons, but you're using 15 meters of rope. So let's calculate the work being used to do this. We know that work is equal to F times D times cosine theta, but theta here is equal to 0 again, because the force and the displacement of the rope is the same. So our force, it's just going to be basically force times distance that we're interested in here. So the force is equal to 30 newtons. The displacement is 15 meters. This is going to give us a joule value. 30 times 15 is 450. You can see that we're using more energy to lift this up than if we just, with a pulley, than if we just lifted it straight up in the air right from the ground without the pulley. This is the useful energy. This is how much energy we're using. So if we go back to the efficiency calculation, useful energy divided by energy input times 100% is the efficiency. So 343 joules is our useful energy. 450 joules is how much energy we're putting in. We're going to multiply that by 100%. Doing the math off screen here. That's giving us a 76% efficiency for this pulley system. Still not 100. We're losing the energy in friction because of the way this is working. It is requiring a lot less force to lift the object, but it is still not 100% efficient. I believe that brings us to the end of the lesson. So this lesson does cover a lot of different things. We covered gravitational potential energy, kinetic energy, the law of conservation of energy, as well as efficiency. But I'm hoping that you'll see that because energy transformations are quite easy to talk about, the math is not difficult. You just need to know which formulas to use. That these questions are going to be really relatively easy to do. So there'll be work assigned for this. Please look for that, and we'll see you during the next lesson.